Hi everyone, and welcome to this lecture. Again, in this lecture, I want to talk about matrices a little bit. Then we're going to talk about Gaussian elimination and back substitution and Gauss-Jordan elimination, and kind of see how we can solve systems of linear equations by using matrices and see all the details. The first step I want to talk about, we are going to talk about matrices in details in the next video. However, just to get an idea what a matrix is, a matrix is an array or table of values. So when you write a matrix, you can write it in general form. You can write it like that. You can A11, A12, A1, and these are just numbers. These numbers are called entries or components. And a matrix has rows. So this is row 1, row 2, and up to row m. So we assume that we have m rows and it has columns. So that's column 1, column 2, and column n. So it has m rows and n columns. So this is an m by n matrix. So m being the number of rows and n being the number of columns. When you write a matrix like this is called the expanded form. So, and I put it here for you again, m rows and n columns. You can also write a matrix in compact form. You can just put Aij and put the number of rows and the number of columns. And we know I presents the row and j presents the column. So I is a number between 1 to m and j is a number between 1 to n. If m equals to n, then the matrix is called a square matrix. Note here for you, for a square matrix, the diagonal entries are aii or ajj. So I and j are equal to each other. Little example, if you have a 2 by 2 matrix, so we can write A11, A12, A21, and A22, and as you notice, this is A11 and this is A22. So now going back to systems of equations, so if you have a system like that, this is a 3 by 3 system, 3 unknowns and 3 equations. So we can first write the, well, if I write the coefficient matrix, you just use the coefficients here, 3, 2, -1, 3, 2, -1, 2, -4, 1, and so on. So the coefficients of the variables. And usually this is called A. And you have, of course, the matrix, the constant matrix, which you write the constants. So here in this case, the matrix of the coefficient matrix is a 3 by 3 matrix, and the constant matrix is a 3 by 1 matrix. So, and 3 here, the first one is the number of equations, and here the number of unknowns. Just remember, sometimes we call, if it's a general form, we call that n. So now if you want to write these two matrices together, so you just write, you can put a dotted line here, or I always use a solid line. So this is A, and that's C, A being the coefficient matrix, and let's call C the constant matrix. And the name of this matrix is, this matrix is called an augmented matrix. So, and let's kind of write this down to the size of this matrix is going to be, in this case, is we have again 3 rows by 3 plus 1 columns, which is the same thing as 3 by 4 matrix. Now, going back to matrices, we're going to go over some legal row operations. There are three legal row operations, and we're going to see this a lot. So the first operation is permute or switch two rows, or interchanging two rows. The way you can write it, the general form is Ri, and we interchange to Rj, or I will be using this notation Pij, just stands for permuting two rows, or permuting row I and j. Second legal operation is multiply a row by a non-zero number or a constant, and that constant, I call that alpha here. So again, this is alpha, and alpha times Ri, and gives me, just changes the entries in Ri. So when I put this arrow, that means it's going to change Ri. Alpha Ri becomes alpha Ri. Next operation, the third one, is multiply a row by a row I by a non-zero number and add it to row j. And the way you write that, you say alpha Ri plus Rj, and that's going to change Rj. So now I put a little example here for you. This is a 2 by 2 matrix. These are the entries. So what I can do, the first operation, I can say 1 over 2 times R1, or R1 divided by 2. This is the same thing, and that's going to change R1. So you take every entry in R1 and you divide it by 2. 2 divided by 2 is 1, and 4 divided by 2 is 2. Second row operation I did with this matrix, I want to make that 0. So I said here, starting from here, I can multiply R1 by -3, because that's 3, and add it to R2. So you write -3 R1 plus R2, and that's going to change R2. And you do it with each single entry, -3 times 1 plus 3 for that one. And you just say -3 times 2 plus 5 for this one. And if you do that, R1 doesn't change, same thing, and R2 becomes 0 and -1. Here I put P1, 2, it's just interchanging or permuting row 1 and row 2. So that becomes row 2, and that becomes row 1. So these are the legal operations. Why do we use this? We use this, well, first of all, in this lecture, to solve a system of equation. So going back to our system, so we had given this system, you write the matrix of the coefficients. So this is the augmented matrix, which is the matrix of the coefficient plus the constant matrix. Our goal, we start from up here, our operations, and we go down. And what we want to have, this is Gaussian elimination and back substitution. Of course, I'll show it to you. The goal is to have 1 in the diagonals and zeros in the lower triangle. And here you're going to get the question marks are just numbers. So that's what our goal is. So let's see how that works. First, I want to make this 1. If I want to make that entry 1, that means that one, I can just permute row 1 and row 3, because row 3 has a 1 here. If I do that, then row 1 becomes 1, 3, 2, 2, and row 3 becomes row 1, 3, 2, -1, and -1. Then I want to make that 0. How can I make that 0? This is 2, so I can do -2R1 plus R2 and change R2. For each one, -2 times 1 is -2 plus 2 is going to give you 0. -2 times 3 is -6 minus 4 is going to give you -10. -2 times 2 minus 1 is going to give you -3. -2 times 2 is -4 plus 8 is going to give you just 4. Next, we want to make this 0. So again, that number is 3, so we can do negative 3R1 plus R3 with each entry. Negative 3 times 1 is negative 3 plus 3 is going to give you 0. Negative 3 times 3 is negative 9 plus 2 is going to give you negative 7. Negative 3 times 2 is negative 6 minus 1 is going to give you negative 7. Negative 3 times 2 is negative 6 minus 1 is also negative 7. Then again, we want to, our goal is to make, what we can do is to make this one first. So if we divide everything by 7 here, then by negative 7, then we get 1s, which is going to make it, that's a legal operation. So let's go ahead and do that. Negative 1 over 7 times R3, and if we change that, we get 1, 1, 1. However, what we want is that 1 to be here. So we can interchange R2 and R3, or just write P2, 3. So we get 0, 1, 1, 1, and 0, negative 10, negative 3, and 4. All I did is just interchanging these two rows. Now, once you get that, then you want to get that to be 0. So you can do positive 10R2 plus R3 by using that. So that stays 0. 10 times 0 is 0 plus 0 is 0. 10 times 1 is 10 minus 10 is going to give you 0. 10 times 1 is 10 minus 3 is going to give you 7. And 10 times 1 is 10 plus 4 is going to give you 14. Finally, the last operation, we can do 1 over 7 because we want to make that 1. And as I told you, we want to see 1s here and 0s here. So if we divide row 3 by 7, or 1 over 7 times row 3 is going to give me 7 divided by 7 is 1, and 14 divided by 7 is 2. So we achieved our goal. 1s in the diagonal and 0s in the lower triangle. So if I go back and write the system for this matrix, we get x plus 3y plus 2z equals to 2 from here, x plus y equals to 1 from, actually y plus z equals to 1 from here, and here we know z equals to 2. After that, it's pretty straightforward. So if you go to number 2 and substitute z by 2, you can solve for y. If you go to number 1 and substitute y by negative 1 and z by 2, and you isolate x, you get 1. So the solution is 1, negative 1, and 2. You can write the solution also like this in a matrix form or in a vector form. So these are all the same thing, which is 1, negative 1, and 2. And be patient, I'll tell you when we use that. So these are called the solution vectors. A couple of notes here. In the example, we had a unique solution. So that was a unique solution. The original matrix and the final matrix are called row equivalent, and every matrices between are all row equivalent. So whenever you do a legal row operation to a matrix, the resultant matrix is row equivalent to the first one. The algorithm process is called row reduction. I'm going to use RR, so please remember this. Then I do RR, that means row reduction. Now that was Gaussian elimination and back substitution, the method we used here. Now let's look at the Gauss-Jordan elimination. So we can go back to this matrix. So the final matrix we got from Gaussian elimination. So this is what we have. However, what we can do is to make the upper triangle also zeros. So the way you can do that, you can start with here. and you can do negative R3 plus R2 to make that 0. So 0 plus 0 is 0, 0 minus negative 0. You put a negative 0 plus 1 is just 1. Negative 1 plus 1 is going to give you 0, and negative 2 plus 1 is going to give you negative 1. Next, we want to make that 0. So we can do negative 2R3 plus R1. And if you do that, since these are zeros, these two don't change. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 2 is negative 2. And finally, we can make that 0 by doing negative 2R1, because we have a 1 here, plus negative 2R2 plus R1. And be careful when you do an operation, you don't want to change all the zeros that you made from the previous operation. So if you do that again, negative 3 times 0 plus 1 is 1, negative 3 times 1 is negative 3 plus 3 is 0. Then this one is just 0. Negative 3 times 0 is 0 plus 0 is 0. Negative 3 times negative 1 is negative 3 minus positive 3 minus 2 is going to give you 1. And guess what? If we have all ones and the rest of the entry is 0, we know that x will be 1, y will be negative 1, and z will be 2. And let's double check the answer we got before, which is the same answer. So Gauss-Jordan elimination, basically your final matrix, you want to see that for the coefficient matrix, all zeros except on the diagonals, all ones in the diagonal. Now here again, we got a unique solution, but let's look at to some other possibilities. Let's say I have this system, and we write the augmented matrix. And here, if you perform the row reduction, which I didn't do it step by step, but if you do it, it's pretty fast. And but you get your final matrix, and I put RR. The row reduction of this matrix is going to give us that matrix. Little notes: when in a column you have 1 and the rest of the entries are zeros, it's called a pivot column. So here we have 2 pivot columns. The first one for X and the second one for Y. The third column is not a pivot column. So whenever you have a pivot column, then the variables are called basic or leading variables. So in this case, X and Y are basic or leading variables. Second note, C1 is not a pivot column because we have negative 1 and 2 here. So therefore, Z will be a free variable. So a non-pivot column gives you a free variable. That means what you can do is call that to be a parameter. So let's see what happens to the solution. If I go back and write this matrix, I write the system for this matrix. So we have x plus 2z equals to 2, and x minus and y minus z equals to 0, which I did here. In this case, we can let, because z was a free variable, it's a non-pivot column, you can let z to be t. And then if you isolate x and y, then you get x is negative 2z plus 2 from here, and y equals to z. And z is free variable, just call it free, which is a real number. So if we write the solution in vector form, we get for x negative 2t plus 2, y is just z, or y is also t, and z is t. Now please pay attention to this because we're going to use this in the next lectures. I can separate those. So you can first take the t's or the numbers with the t coefficient. So we have -2, here we have t, and here we have t also, plus, then we can put the constant there. The x has a constant, so I put 2, but this one does not have a constant term, or this one does not have a constant, you just put 0. So that, if I take that and add it to that, I get the same solution. And again, be patient, we'll see why in the future this is useful. Or in a matrix form, you can say x, y, z equals to t times -2, 1, 1. So from here, plus 2, 0, 0. So this is again, the vector solution. Couple of notes here. Note 1, this system, when you get this system has infinitely many solutions. Note 2, why that happens, because number of pivots is less than number of unknowns. So number of pivots, I call them rho. So let's just remember, whenever I use rho, that means number of pivots. Number of pivots for this system, we had 1, 2. And number of unknowns, we had just 3 unknowns. That was 3. So for this one, if I write this, we had 2 was less than 3. So when that happens, that means the system has infinitely many solutions. Let's look at other possibilities. So, and I think this is the last one. Let's say you take a matrix, an augmented matrix, you do the row reduction or all the row operation, and that's going to give you the final matrix. One thing to notice in the final matrix, when you get that, the constant matrix is pivot, or the constant column is pivot. So if I write this back, just that row, 0 times x plus 0 times y plus 0 times equals to 1, and we know 0 is not equal to 1. So therefore it's no solution. Important note, if the constant column is pivot, the system has no solution. So the system is inconsistent. So let's go over the summary of what we did, and I think that's going to make it very fast and easy to follow and understand. Let's say we have a system, and when I write this, that means this is the augmented matrix. A is the coefficient matrix, which is n by n, and C is the constant matrix, like we saw on the top, all those matrices. So the start, so this is A, and that's C. So let's see what happens when we do the row operations or the row reduction. After RR, if there is no pivot in the last column or in this column, then the system is consistent. If there is a pivot in the last column, then there is no solution. The system is inconsistent. So, and when the system is consistent, if rho equals to n, that means the number of pivot equals to the number of unknowns, then you are going to get a unique solution. If rho is less than n, just like we saw in the example, then you're going to get infinitely many solutions. And in this case, the free variables, if you want to know how many free variables you have, you can just do n minus rho, and that's going to give you the free agents or the free variables. One more time, rho is number of pivots. Now, next I want to talk about homogeneous systems of equations. That happens when the constant column has only 0 entries. That's an example of that. So the constant column is 0. Therefore, that means therefore, for a note, if we do the row operations, we're not going to get a pivot in the last column when they're all zeros. So there's this system, a homogeneous system, is always consistent. Now, what happens? Number one, If rho equals to n, then you're going to get a unique solution. If rho is less than n, then you're going to get infinitely many solutions. And there is one solution which is always obvious or trivial. We call that the trivial solution all the time, and that's when xi's are 0. So what do I mean? X1 equals to x2 equals to x3 and equals to xn equals to 0. And obviously, if these are zeros, in each equation, you're going to get 0 equals to 0. So 0 is always a solution for a homogeneous system, and that's called the obvious or the trivial solution. Most of the time, we are going to call it the trivial solution. So now there is a theorem or a note. Every homogeneous system is consistent if the system has fewer equations than unknowns, then it has infinitely many solutions all the time. So less equations than unknowns, then you're going to have infinitely many solutions. Maybe I should write. So if you have like a system x plus 2y plus z equals to 0 and 2x plus 4y minus 5z equals to 0. We have less equations than unknown, so this system will have infinitely many solutions if you solve it. How do you solve it? You can just go ahead and do Gaussian elimination and rewrite the system, and you're gonna find out the pivot columns and the non-pivot columns. Non-pivot columns are gonna be your free variables, and the pivot columns are going to be your leading variables. So, and I guess that's it for this lecture. And next time, in the next lecture, we're gonna see row reduced or row echelon form for matrices. Thank you, and I'll see you in the next lecture.